Hello. In this lecture, we're going to begin a brief discussion of differential equations before the semester is over. Now, in a typical Cal 1 type of course, you would not encounter too many differential equations, but because this is targeted at data science majors and it's kind of a mix of Cal 1 and Cal 2, I'm going to give at least 2, maybe 3 lectures on differential equations. This topic is actually, it's very important. It's very applied. Differential equations on its own is a field of mathematics that is applied to finance, physics, chemistry. It's one of the most applied fields in mathematics. And it's even applied in some aspects of data science. And actually, interestingly, I just saw an article last week that uses deep learning to help solve differential equations, because sometimes you can't even solve these things, which I should probably write down the definition of what a differential equation is. So let's go ahead and do that. So definition. So a differential equation in x and y is an equation that involves x, y, and derivatives of y. And these derivatives of y can be first derivatives, second derivatives, it doesn't matter. So this is the definition of a differential equation. Now, the solutions to a differential equation are not numerical, but they're functions. So if you're given a differential equation, the solution is an actual function. So maybe I should write that down. Maybe I'll write down what they have in the textbook, I suppose. A function y equals f of x is a solution to a differential equation. If the equation is satisfied when y and when y and the derivatives of y are replaced by f and the derivatives of f. Replaced by f of x and the derivatives of f of x. Fit it in there. Just can't see it, but derivatives of f of x. So, for example, the best way to illustrate this is to say maybe let's look at y prime plus 2y is equal to 0. Okay, so this is a differential equation. There are no x's here. There's just y, but y is treated as a function of x. Okay, so what would a solution to this be? And so what's a value for y that if I plug in, I take the derivative, I get 0? Um, well, maybe one such solution to this could be y is equal to e to the power negative 2x. So why is this a solution? Well, if I replace y prime by the derivative with respect to x of y, that's y, and I have plus 2y. Does that equal to 0? So the derivative here is going to be, oh, I need to replace y by what it is, e to the negative 2x. So then derivative here is going to be negative 2e to the negative 2x plus 2e to the negative 2x. And that does equal 0, so that is a solution to that differential equation. But wouldn't it also be the case that another solution would be maybe y is equal to 4e to the negative 2x? That's also a solution, right? Because if we do the same procedure, 4e negative 2x plus 2 times 4e negative 2x. This becomes negative, so take this here to negative 8x, negative 8e to the negative 2x. 2 times 4e to the negative 2x is 8e to the negative 2x. That does indeed equal 0, so that's another solution. In fact, the general solution to this differential equation so for this given differential equation is just y is equal to c times e to the power negative 2x, where c is just some real number. Okay, so that's the general solution. So what this points out is that differential equations can have many solutions. In general, they can have many solutions. Infinite solutions. Right, there's infinite solutions here. For any value c, there's a solution. Okay, but as we'll see in a bit, there will be instances where unique solutions will occur when we're given initial values that the equation must satisfy. Okay. Okay, so let's look at like another example here. So let's look at the second. Oh, I should probably write this down before I get to the example. The order of a differential equation how did I write this down? So the order of a differential equation is determined by the highest order derivative in the equation. So for example, this would be a first order differential equation. Because the highest derivative in this equation is the first derivative. So this would be a second order differential equation. Second order differential equation. Okay. So just so that we understand how this works, let's look at possible solutions to this equation. Y is equal to sine of x. Y is equal to 4e to the power of negative x. And let's just use these two. So which of these are possible solutions to this differential equation, the second order differential equation? Well, we just plug in, we take the derivatives and see if it works out. So for this one, we get, so if that's y, then y prime is equal to cosine of x, and then y double prime is equal to negative sine of x. Right? So then if we plug in, we get negative sine of x minus sine of x equals negative 2 sine of x, which doesn't equal 0, so this is not a solution. What about here? So then what's y prime in this case? It's negative 4e to the negative x. And then y double prime is equal to 4e to the negative x. So it looks like this one is going to work, because then if we plug in, we get, so y double prime is 4e to the negative x minus y, which is just 4e to the negative x equals 0. So that is one solution to that second order differential equation. Okay. So I'm going to go ahead and pause it, clean my board, and then we're going to do some more. Okay, so I almost forgot to mention that when we find a general solution to a differential equation, what we're really doing is we're finding a family of functions that are the solutions to this equation, or the equation in question. So what does a family of functions do in R2, for example, in the plane? This collection of solutions is going to be a collection of curves, right? So, for example, so let's just like state this formally. The general solution to, or maybe of a first order differential equation okay, so this is some infinite collection of functions, possibly infinite, something more than one, as we've seen. So the general solution of a first order differential equation represents a family of curves. So for example, we just did an example where y prime plus 2y equals 0 has a general solution y is equal to c times e to the negative 2x. Right, so that's the general solution of that differential equation. Now, for each value of c, we have a curve in the plane. So, for example, when c is equal to 1, what is it? So, c is equal to 1, and x is equal to 0, we're at e to the negative 2, so probably like down here. And when c is equal to negative 1, no, so when c is negative 1, we're down here. When c is positive 1, we're like right there. So like, here's like c equals to negative 1. And then like here is c is equal to positive 1. But then for c is equal to positive 2 and c is equal to negative 2, we also have like, if for any choice of c, we have this family of curves. Now, this can be useful to model physical phenomena. Like we're about to mention here in a moment slope fields, but imagine like you have like wind going over like an airplane wing. You can probably model that, no, not probably, you can model that with a set of solutions to a differential equation. Okay, so there's a lot going on here. When we find general solutions, we're finding this collection of curves that is modeling or can model a lot of different things. Now, this is in the general setting, but sometimes when we're solving an equation, we have a particular solution that is enforced by conditions that the equation must satisfy. And I guess I'll state that formally here. So, like a particular solution okay. So a particular solution of a differential equation is enforced or is determined by what are called initial conditions. So I say determined. By what are called initial conditions. So now, provided you have initial conditions, your solution will go from this family of curves to a particular curve. Now, what would be like, why is it called initial conditions? Why would we want to do this? Well, suppose like we have some position that we're measuring, and we measure that we have like the acceleration for a given time t is equal to negative 32 feet per second or something. I hate that your textbook uses feet and not meters, but suppose we're measuring acceleration as negative 32 feet per, negative 32 feet per second. Okay. And so a general solution to this, differential equation this is a second order differential equation. There's no variables, so we could say we can verify that S of t is equal to, so what should this be? Negative 16 t squared plus c1 times t plus c2. We can verify that this is a general solution to this differential equation, right? If we take the first derivative, we get negative 32t plus c1. Take the second derivative, we get negative 32, nothing else, right? But so suppose we're measuring like acceleration or something like this as negative 32 feet per second, but we also observe that at time is equal, so this is with respect to time. So we observe that the distance at time equals to 0 is equal to 80, and the velocity at time is equal to 0 is 64 feet per second. This is 32 feet per second squared. This is 64 feet per second. Okay, so these conditions, these observations enforce that the C1 and the C2 here have to be a certain value. In particular, we get that this implies that C2 must be equal to 80. Because when t is equal to 0, that's 0, that's 0, you're left with that. C2 has to be equal to 80. And this implies that C1 has to be equal to 64. Right, because the first derivative is negative 32t plus c1. When t is equal to 0, that goes away, you're left with 64, so c1 has to equal 64. So the particular solution that these initial conditions imply, so these are the initial conditions, in particular solution. We just plug in that and that into the general solution. So S of t is equal to negative 16 t squared plus 64t plus 80. So that would be the general solution to that differential equation under these initial conditions. So just to really emphasize that these are the initial conditions. Okay. Okay. So unlike algebraic expressions where in many instances we can find the solution, differential equations are typically very hard to solve, especially when you generalize this notion to what are called partial differential equations, and you have no idea if there's a solution in some instances. So that's like, I should probably make a note of that. In general, differential equations are difficult to solve. Or impossible to solve analytically. So analytically is like by using these techniques to just work out what the solution should be. Okay, so that's a difficulty of this subject. That's why it's its own field in mathematics, because it's not some easy to do thing and it has applications all over the place. which I found it fascinating, by the way, going back to what I mentioned at the beginning of the lecture. They're difficult to solve, but recently people used deep learning and neural nets to find solutions to differential equations, which I think is really, really cool and very interesting. Okay. Okay, so we're not going to do that, but we're going to note that, and we're going to have two techniques to kind of approximate solutions or to get ideas on how the solution might look, even though we might not have the tools to solve it ourselves. So I would say one possible way is to look at slope fields. So what is a slope field? So let's just consider the differential equation y prime is equal to, can you see that? Yeah. Y prime is equal to 2x plus y. So even if we don't know what the solution or what a solution to this differential equation is, we can get a sense of the behavior of this function because we know the derivative of the function, right? How many times in this class have we always gone back to what the derivative can tell us? If we have an x and a y, we know the slope of the function at that point. So for example, so x, y prime. So when these are both 0, that's 0. When x is 0, y is 1, y prime is 1. When x is 1 and y is 0, then y prime is 2. When x is 2 and y is 1, y prime is 5. What we're doing is we're looking at points, and then we're looking at the slope of the tangent line at those points. So for example, at 0, 0, the slope is 0. There's a different color, red. Can you see the red? When we're at 0, 1, so 0, 1, the slope is 1. When we're at 0, 2, the slope is 2. 0, 2 is just a little bit steeper there. We're at 0, 3, it's a little bit steeper. Okay. We're at 1, 0, the slope is 2. So 1, 0, slope is 2. We're at 1, 2, the slope is 3. When we're at 1, 3, the slope is 5. And if we start connecting all of these curves together, well, let me do the over here. It's like when x is -1 and y is 0, the slope is -2. So it's like that. When x is -1 and y is 1, slope is like -1. And if we plot all of the tangent lines, we start to get a picture of what the possible solutions look like. Now this is definitely where like for example, like magnetic fields can be modeled with differential equations like this. Okay. Not exactly like this, but similar, right? So you can see the curvature here can somehow describe physical behavior, flow, force, right? Direction of vectors in a vector field, which you'll learn what vectors are next semester. But yeah, so these are ways to just visualize the solutions. Okay. Now, the next way that we're going to look at approximating solutions or trying to figure out what the solutions look like is called Euler's method. And that will be a separate video because I think it should be on its own. So I'm going to go ahead and stop this recording here and then pick back up with Euler's method.